Yes, I want to talk about genetic algorithms in general, a little bit. Yes, better. I want to talk about genetic algorithms. My cable is a little bit broken over here, which I don't think matters too much. But you can get that. Okay. You like Rosa? No. Okay, basically it's about creating functions which are encoded in a genome. And I put here up some slides. It's a page on the internet. You can watch it and read the text also about it. And you see here, it's a genome and it encodes an expression tree which is below here. It doesn't matter which operators you use. They can be binary or unary operators. And the idea is just to have any function encoded in such a genome and to use it as a cipher algorithm. There are some operators, some genetic operators, which can be applied to such lists of symbols, actually. There is mutation, where you can mutate a single symbol, like here, and replace it by another one. And one has to distinguish between the terminal symbols, like a variable or a constant, and binary or unary operators, like plus or the multiplication. And there's also transposition. It's like here, a part of the genome, the part of the gene is moved upward or downward in the gene and produces a totally different expression tree in that moment. And things like crossover, this is like in nature. It's like they found it in the biology, and it can be applied in the computer science, where two genomes cross each other. We have form a genome pair like this one here, and then they cross each other and exchange information like here. And then there's replication, where the genomes are replicated without modification. And so we create a population of such expression trees encoded in these genomes. And we have a basic algorithm about that. It's here. It's a program control flow. First, we seed the individuals. That means we just put lots of symbols into a genome. They are random, and we try to keep the expressions valid so that they can be evaluated later on. And we enqueue them into a priority queue, first of all. And this is the key to the idea of the cryptographic algorithm, because we need to know which of the individuals we have fit best into the population we have. Because we have to filter out the not so good fitting individuals, and to operate and use the genetic operators on the well-fitting ones. And if we have such a priority queue where they are ordered in a good well-fitting manner, we can extract them and create the expression tree and evaluate the fitness of those individuals. And this is done like we iterate over the function, over the expression tree, and create a pattern of numbers. And this pattern of numbers, they can be all zeros. For example, if the first element in the genome is a 0, then the individual only produces 0. So this is not a good cryptographic algorithm.
1 minute left.
Yes, okay, thank you. We have, therefore, we use the Huffman code, which we pack the pattern which is generated, and the worse it packs, the worse it compresses the code, the better is the entropy in the pattern which was produced, and we can consider this as being a good cryptographically good individual. So if we sort them by the Huffman code size, we can do the replication and mutation and transposition again and again, over and over, and create the a population of good cryptographically strong algorithms, actually. Yeah, that's the key idea in it, that you use a Huffman code to have the fit ordering.
Sorry, your time is up.
Yeah, thank you.
Are there any questions? Apparently not, so thank you for your speech. The next